On the periodic table, each element has an, whoops, I typo there, average atomic mass. And so we've talked about this in like unit 4, right? We have isotopes, so our atoms can have all sorts of different weights, but the red number with the decimal on the periodic table is the average of all the isotopes that are possible. And so the units that we give to these are called AMU. AMU stands for atomic mass unit, and that is just defined as the mass of one proton. So they figured out, okay, a proton weighs this much. Obviously, this applies for a neutron too. They weigh the same. So we're just going to say that's an atomic mass unit. And so using carbon as our example, we know that carbon has an average of 12 atomic mass units per atom. And so knowing that it weighs as much as 12 protons, that is a tiny small number if we were to think about grams, right? So it would be so impractical to talk about one atom of carbon. Plus, it's very odd that we would be working with just atom, right? There's tons of different atoms of carbon throughout our whole body. So what if we weigh 12 grams of carbon? Then we'd want to figure out how many atoms we have. And what's odd, you could do this with any mass of any element and you'd get the same answer. How many atoms does its atomic mass have? It's the 6.02 times 10 to the 23rd atoms. So you don't necessarily have to be like completely understand what I'm explaining here. But again, like if we were to take helium, which has an average atomic mass of 4, if you weigh out 4 grams of helium, it also has 6.02 times 10 to the 23rd atoms. So this is just a very special number that you guys are going to get familiar with for doing calculations. And so I'm going to try to break this down with math here. If we know one atomic mass unit weighs one proton, therefore weighs the same as one neutron, right? And so if you convert this mass into grams, well, one atomic mass unit would be equivalent to 1.67 times 10 to the negative 24th gram. So that's a very, very small number. All right. So let's use carbon. If we know carbon weighs 12 atomic mass units, what we're going to do actually is a conversion, and we're going to convert it from AMU to grams. So for every one atomic mass unit, we're putting that on the bottom so that it cancels. That weighs 1.67 times 10 to the negative 24th grams. So we're bringing back some conversion factors from unit 6 here. So if I define a relationship, I can write it as a fraction with 1 on the bottom and 1 on the top. Doing this calculation, you would get 2.00 times 10 to the negative 23 grams. All right, so that is how much one atom of carbon weighs. Now that we know how much one weighs, let's figure out how much that fancy little number, 6.02 times 10 to the 23rd atoms weigh. All right, so if you have 6.02 times 10 to the 23rd atoms, this mass that we just found is technically per one atom of carbon, right? So we can use that as a conversion factor as well. So as we set up, I'm going to make sure to put my one atom of carbon on the bottom, again, making sure that the bottom cancels out with the front number. Because remember, you can think of this over an imaginary 1. And then the top number is that 2.00 times 10 to the negative 23rd grams. Doing that calculation, guess what? 12 grams. So this is just a proof that in the mass, the average mass in atomic mass units, if you weigh out that in grams, that's how many atoms you have for everything. You always have this 6.02 times 10 to the 23rd number. And this is all thanks to Avogadro. He is awesome. So yeah, we get to talk lots about him. And you get to see his little cutout I have of him during class this unit. So Avogadro's number. And then we're going to define this as a mole. So it's like a dozen, right? If I say you have a dozen eggs, you have 12. If I say I have a dozen pieces of cheese, I have 12 pieces of cheese. If I have a dozen cars, I have 12. That's what the mole is for us. If I say I have 1 mole of carbon, I have 6.02 times 10 to the 23 particles of carbon. If I say I have 1 mole of sodium chloride, that's how many particles I have of it. So it's just like a generic term so that we don't have to keep writing this number over and over again. We can just call it 1 mole. All right. So in chemistry, mole is a unit, not the animal. All right. So let's move on then. Talking about the atomic mass, we're going to use silver as an example. And again, we say that there are 107.9 grams of silver. We will have that 6.02 times 10 to the 23rd particles. So we call this molar mass, which hopefully you guys think that is named well because it's the mass of 1 mole of substance. Every single substance has it, and it's all based off of the numbers off the periodic table. So molar mass is defined as the mass of that many particles, which obviously is the mass of 1 mole. And so you are going to be using the number in red off the periodic table. All right, those are the ones with the decimal. And what it's going to end up having then are these fancy units of grams over mole. So we actually shorten mole because, like I say, scientists are lazy. It's too much to write that extra E. So we shorten mole, the unit mole, to MOL. What we're going to do for simplicity is always round to the nearest tenth off the periodic table. All right? So let's just do some examples. So if you were to look right now at the periodic table on element number 2, atomic number 2, helium, you would see its mass in red, and rounding that to the 10th place gets us 4.0. We give it units of G/MOL. But I want to make note, because we're going to have to use conversions with these later, that when I write a unit G/something, it's the same as saying, hey, we have 4 grams for every 1 mole, right? And that's its definition. Looking at oxygen, we would find its number in red and round to the 10th, we'd get 16.0 grams per mole. And lastly, lead. So if we were to look at lead number 82, you guys try and write down what this would be rounded. All right, well, hopefully you guys found that number. What you should have gotten is 207.2 grams per mole. So it's really simple to find the molar mass. So this is of just an individual element or an atom. Now let's practice doing it when we have molecules or formula units. So our first example here is just hydrogen. All right, so we know it's diatomic. So how you do this is you guys, again, should be pros at counting quantities of atoms, especially after balancing and whatnot. So what we can see is we have 2 atoms of hydrogen. So all you do is just multiply 2 times the mass of 1 hydrogen, which is 1.0. And so the molar mass of hydrogen is 2.0 grams per mole. All right, now moving on to one that has 2 different types of elements, you break it down. So we have 2 hydrogens. So again, we're doing that 2 times 1.0, but then we're going to add the mass that is also coming from oxygen. So we only have 1 of them, so we don't have to multiply it by anything. So 2 times 1 is 2, plus 16 gives us 18 grams per mole. All right, the next one here. So we have calcium chloride. So in our case, calcium, we only have 1 of them. So again, do not have to multiply. So 1 calcium weighs 40.1, and we will add that to 2 times the mass of chlorine, which is 35.5. So again, I'm making sure to round all of my masses to the 10th, and then I add up all my contributions from all elements. This gives me a total of 111.1 grams per mole. All right, I want you guys to try the next one here. Try doing potassium bromide. So go ahead and pause, and then when you've tried, resume. All right, what you should have found is potassium weighs 39.1, and you are going to add that to the mass of a bromine, which is 79.9, Neither of them need to be multiplied because it's a 1-to-1 ratio. You end up getting 119.0 grams per mole. Now, these last two are a little more difficult, but I hope you will find that they're still simple. So in this case, we have multiples of all of our atoms. We have 6 carbons, 8 hydrogens, 7 oxygens here. And so how would we find this is multiplying 6 times the mass of carbon, which is 12.0. You're adding that to 8 times the mass of hydrogen, 1.0. And then add that to 7 times the mass of oxygen, which is 16.0. So again, just kind of labeling over here, this is how we find the mass from carbon. This is how we find the mass from hydrogen. This is how we find the mass of oxygen, and we are adding that all up together. After multiplying and adding, of course, you guys should know PEMDAS as well, you will find that the total is 192.0 grams per mole. And the last one here, again, looks complicated, but you guys are pros from balancing. You should know how to distribute subscripts to the atoms here. So just as if like we were doing a balancing, we were going to be doing an atom count like this. So the way that you would figure out the number is you distribute that 2 inside the parentheses. So really what we have is 3 magnesiums, 2 phosphorus, and we are multiplying, so we have 8 oxygens, all right? So those are just what we're multiplying their masses by. So what we get is 3 times the mass of magnesium, which is 24.3, plus 2 times the mass of phosphorus, which is 31.0, and then adding that to 8 times the mass of oxygen, which is 16.0. And then we get a total of 262.9 grams per mole. All right, so that's how we find molar mass. Now, if we don't have 1 mole of something, we are going to be using molar ratios, all right? So we'll just call them mathematical ratios for now, but you could pretty much logic through them. And so we'll get more into this next class period. But if we have half a mole of something, then we have half the amount, right? So if we only have half a mole, then we have half that number of particles. So you just half it, right? If we have twice as much, then we have twice that number of particles, okay? So this is going to be similar for mass, right? If these are all our masses for 1 mole, if we have, for example, half a mole of water, guess what? It weighs only 9 grams because that's half of 18. So hopefully you guys will get really familiar with the relationship between a mole and its mass. And yeah, we'll keep working at it. And